I will begin. Heavenly Father, we thank you for this day again. I thank you for the students. Just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. All right, so do you guys have any particular questions about the homework? For instance, before I get into the other stuff, if you got questions, you could ask them. Well, all right. If you think of some, you can ask. All right, but here's one theorem that I probably should prove for you guys. If S is an orthonormal set in V with inner product, then the matrix of S is orthogonal for F equals to R. And I have a suspicion, I'm not sure about this, but I think it's unitary in the case that the field is the complexes. All right, so let's just talk about that. That's really, I want to make sure that I communicate to you guys today. Oh, okay, so like O, N are the orthogonal matrices. This is the set of, let's say R in Rn by n, such that R transpose R is equal to the identity. All right? These are the so-called orthogonal matrices. There's other notation that I should mention, like SON. What's that? There's one added condition. SON is you have orthogonal matrices which are also determinant 1. All right? That's orthogonal matrices. And unitary matrices, on the other hand, complex matrices. So U, and I don't usually write C, I just write UN typically, I guess. I don't know, I don't talk about it enough to have solid choice for notation. But, not R, but C n by n complex matrix, such that U dagger U is equal to the identity. This is the set of unitary matrices. And so SUN, what do you think that is? So you've got the unitary condition, U dagger U equals to the identity, and what else? Determinant U equals to 1, right? So the S stands for special. So these are also known as the SUN is the special unitary matrices, and SON is the special orthogonal matrices, if you like. Right? What can you guys tell me about the determinant of an orthogonal matrix? If we take the determinant of R transpose R equals to the determinant of I, that implies what? since the determinant of the product is product of the determinants, and the determinant of the transpose is equal to the same, right? We get the determinant r squared is equal to 1, which tells us the determinant of r is what? Looks like plus or minus 1, right? So it turns out that the orthogonal matrices come in two flavors, basically. Determinant 1 and determinant minus 1. That's all there is. So in terms of like, you could write this as SON R unioned with, we could use the notation minus SON R, if you like. Yes, SON is a subgroup. And yes, that is a disjoint decomposition into two equally sized sets, although these are infinite. But I think it's true that ONR mod SONR is Z2 up to isomorphism if you're taking abstract algebra while you're taking the course which is the prerequisite for abstract algebra. If you were to do such a thing, that comment would be in place. Otherwise, it would be a ridiculous comment. So anyway. But yeah, so there's the orthogonal matrices. They come in those two flavors, right? Now, UN, what's the condition on the determinant of a unitary matrix? U dagger U, right? But notice that that's the determinant of U conjugate transpose, all right? Think about the formula for the determinant. How does complex conjugation play with that? Like, what is a determinant? It's a multinomial in the components of the matrix, right? It's a sum of products of n-fold copies of components of the matrix, an n by n matrix. And the thing about the complex conjugate is the complex conjugate of a sum is the sum of the complex conjugates, and the complex conjugate of a product is the product of the conjugates. And so if you sort through that, what that means is that this is really the determinant of U transpose conjugated. So that then gives us the determinant of U complex conjugate times the determinant of U is equal to 1. But what is that? That says the modulus as a complex number of the determinant of U is equal to 1. So that means that these are quote-unquote unimodular. Unimodular. They have modulus, which is unit 1. They're length 1. The determinant's length 1. I don't get to say plus or minus 1, though, right? It's much more complicated. All right, so now we have in front of us what is the definition of an orthogonal matrix and also the definition of a unitary matrix. What do you think about my theorem? Can we prove it? What do you think? So the matrix of S, right? Column J of that is what? Oh, my bad. Blarg. I am assuming for this theorem to make sense, I'm going to assume V is equal to Fn. Sorry about this, guys. But I mean, I'm thinking Fn for the... Otherwise, I'd have a matrix of abstract vectors, which is something you could think about, but I'm not ready to think about it today, so I'm not going to do that. But if I do this, column J of the matrix of S is literally, by my construction, Vj, right? I mean, this is, which is an n vector, right? So just to be clear, this matrix is V1 glued together with V2. You keep gluing until you get to the nth one. So how do we calculate the, what's the ijth component of S? Uh-oh. So I believe it was the inner product of, well, fine. In my current notation, it would be EI transpose matrix of S oh. I mean, this is just true for a matrix in Fn by n, right? Oh, anyway, this isn't what I need to look at, is it? What am I supposed to be looking at? I mean, this is not wrong. It's just not helpful. I'm trying to. I want to show that if I have, I want to look at S transpose times S, right? I'd like to show that. I want to show that that's the identity matrix. That's what I'm trying to prove, right? I'm trying to prove that. Let's stick with the real category to start with. I know it's true there, all right? And then we'll try the complex. Let's keep it real for the moment. So I'm trying to show that the matrix of S is an element of O and R, right? And I'm assuming that S is an orthonormal set. Okay, so you guys tell me, what is the ijth component of this matrix equal to? Taking you all the way back to 221. Still matters, right? What's your go-to formula for matrix multiplication? You take the ith row of the left factor, right? Dot product with the... Right, so we do row I of the matrix of S transpose dotted with column J of the matrix of S, right? But what is the ith row of the transpose of S?
The column of S.
Exactly. So it's the ith column of S, right? The jth column of S, which of course is what? That's literally vi dot vj, which by the way is Kronecker delta ij, because we assume that we're working with a orthonormal set, right? So we've done it, right? Therefore, S transpose S is equal to the identity. Yay! Hence, the matrix formed by gluing together an orthonormal set is in fact a orthogonal matrix. And also, while I've stated this in the if-then sense, look at these calculations. Are they reversible? Like if I give you an orthogonal matrix, right? And then you just make a set by stripping out the columns of the orthogonal matrix. That resulting set, is it an orthonormal set? It is, because of this calculation right here. If this matrix satisfies that, it's equivalent to saying that the columns of this satisfy this relation, which is to say they're orthonormal. So like the argument's reversible. A real matrix is an orthogonal matrix if and only if its columns form an orthonormal set. What about the complex? What would change it? Is there a question, or we have time if there's a question? How does this discussion change for the complex case? Then, what's the inner product of Z and W what did we say it was? It was Z transpose times what? W conjugate, I think? Yeah. That was how we defined the complex, the standard complex inner product, is right? It's linear in the first entry, it's conjugate linear in the second entry, right? That's why we've got the complex conjugate on the W. So again, we're going to let S equal to V1, V2, Vn, where the inner product of Vi with Vj is Kronecker delta Ij, right? So this is, what was my language for it? Oh, goodness gracious. I want to say, I think he says orthogonal. Do you guys remember if there was a different word other than orthogonal we used for this? I mean, orthonormal. Yeah, I think we just say orthonormal still. It's just I have a prejudice against that usage because when I think orthonormal, I think real, but maybe that's just me. Okay, so our goal is to show what? I'd like to show that the matrix S formed in this way is an element of the unitary matrices, right? So I need to calculate, I need to look at S dagger times S, right? And look at the ijth component of that, let's say. But we know how to, I mean, this argument is much the same as the one we just went through. This is what? This is rho I of the Hermitian conjugate of S. So that's conjugate transpose, right? Dotted with the jth column of S, right? Now, I'm using dot product here, but you could just as well use like the transpose times the other one, it's just that. All right, so this is the same as column I of the conjugate of S dot product with column J of S. But what is column J of the conjugate? That's nothing more than the conjugate I transpose times Vj. Now it's a little bit annoying because what is Vi Vj? By my definition, it's Vi transpose, right, times what? Vj conjugate, right? So what do you guys think? Are we in trouble? Are there things we don't appreciate yet here? Like, what's the deal? There's something I'm forgetting. Oh, did I do something wrong?
Well, probably not. I just this is where the variance
Oh, the dot product is like, you do the transpose of the vector times the other one. So this is like, you know, a 1 by n times an n by 1. That's what I mean by dot product there. They're complex vectors. What do I mean by dot product of complex vectors? I just simply mean the first times the first plus the second times the second plus the third times the third, dot, dot, dot. So in terms of a formula, like if I was to write z dot w, what I mean by that is simply z transpose times w. Now that technically speaking is not a, that is not a complex inner product though. Because we need that sesquilinearity, we need the, you know, I think there's a property, I'm forgetting some quirk of the formula here. It's probably in an exercise in the textbook. Wheel. Oh, yes? Hey, that's not a bad idea. We have, let's do that, because we don't just have these vectors in the abstract. We know this, right? So we know that Vi, Vj is equal to Kronecker delta ij, right? But this is Vi transpose times Vj conjugate equals to delta ij. Now delta ij is 1 or 0, right? So in other words, we can take the complex conjugate of this equation, and what does it tell us? So that is Vi conjugate transpose Vj conjugate conjugate, which is equal to Vi conjugate transpose times Vj. But what's that equal to? Well, it's equal to the conjugate of Kronecker delta ij, which is just Kronecker delta ij, right? Hey, that is where we got to. And that's then equal to Kronecker delta ij. Hooray! So again, the same theorem holds. If you take an orthonormal in the unit in the complex sense with respect to the standard complex inner product on Cn, and you glue those together, it will give you a unitary matrix, and vice versa. So every unitary matrix corresponds to an orthonormal basis for Cn. It's kind of neat. All right. Let me write a theorem down for you guys.
I'm sorry. So was that like an if and only if statement? Because it goes both ways. Like,
Yes, I wrote it as an if-then, but it is in fact, it can be upgraded. If you look at our argument, I think it. Okay, so let's see here. I wanted to write for you guys. Oopsie. A definition and theorem. First of all, the definition. This is from section 6.6 in the textbook. So here's the definition. Let V be inner product space and T, a linear transformation on V, B, a projection we say that T is an orthogonal projection if the range of T, orthogonal complement, is equal to the kernel of T. I mean, he uses R and NN for kernel because his null space and kernel are more, he's kind of conflating them. That's fine, but let's see here. Oh, and the kernel of T's orthogonal complement is equal to the range of T. Now this begs a question, I suppose, right? Which is, what's a projection, right? Do you guys know what a projection is? We covered it, yeah. I think that was part of the discussion about independent subspaces, right? Like, it's in the paragraph right above. He's like, if V is W1 plus W2, then a linear operator, let me write it out. If we have V is W1 direct sum W2, then T, a linear transformation, let me just write it out. T, a linear transformation on V, is projection on W1 along W2 whenever x is equal to x1 plus x2, where of course x sub I is in W sub I, right? We have T of x equal to, what do you guys think? It's a projection on W1, so that means it goes on x1 is what we're looking for here, okay? Now, if this is the case, what's the deal with the kernel? Like this is not, we're not yet in the orthogonal stuff yet, but there's nothing about orthogonality in here necessarily, okay? So like, what's the kernel and the range of this map? Can you tell me? It's outputting x1, right? Which, yeah?
Is it just W1?
W1, right? And yeah, W1 and W2, right? So you see that V is equal to the range of T direct sum the kernel of T. However, it doesn't have to be the case that this plays nicely with the concept of orthogonal complement, right? Like, for example, let's do a two-dimensional example. This could be W1, right? And this could be W2. As, you know, W1 plus W2 is R2, right? However, it's not like this, right? You guys see there, right? What's the orthogonal complement? They're not the same as the W1 and W2, right? Like the orthogonal complement, with respect to the usual Euclid dot product, right? Here is W2 perp, right? It's not equal to W1. And likewise for the other one, right? So if I had T, you know, as a mapping from R2 to W1, we would have that R2 is, you know, the range of T direct sum kernel of T, right? That's true in this situation for the projection, but it is not true that we have what we have up here, right? We don't have that the perp of the range is the kernel and vice versa. So not every projection is an orthogonal projection, okay? But an orthogonal projection is one which not only is there independent subspaces corresponding to the kernel and range, right? They're also perpendicular. Yeah. Okay, so that's the first order of business. Understand what is a orthogonal projection. And once you have that, then we can write down so-called spectral theorem. The spectral theorem is kind of the main event, I would say, of this chapter in some sense. Which I mean, I kind of already spilled the beans last class in terms of the operator is, you know, diagonalizable in a complex inner product space in the orthonormal sense, if and only if it's a normal operator, and a real operator is orthonormally diagonalizable. That's a mouthful. In a real inner product space, if and only if it was self-adjoint. Right. In both of those cases, you have an eigenbasis for your operator. And that eigenbasis, not only that, it can be chosen, it can be selected such that it's orthonormal. Which isn't to say that every eigenbasis you find is orthonormal. It just says that there exists an orthonormal basis. It's eigenbasis. I mean, you've experienced this if you've worked enough problems with eigenvectors. Sometimes you find eigenbasis, but they're not orthonormal, and then you have to like Gram-Schmidt them to perpendicularize them, if you will. So here's the theorem. Theorem 6.25, spectral theorem. And this terminology, spectral theorem, goes back to the history of linear algebra, which is connected to the history of complex quantum mechanics, rather. So suppose T is a linear operator, and V has got the inner product space, finite dimensional. All right. With distinct eigenvalues, lambda 1, lambda 2. We'll say we've got k of them. All right. So we're assuming T normal if the field is the complexes, or T is equal to its own adjoint if the field is real, right? In other words, we're assuming the condition that's necessary to get the eigenvalues and the eigenbasis. All right, great. Let W sub I equal to the kernel of T minus lambda I for, which is, I mean, my other notation usually was E, right? E sub I. Those are the what? we call these what? You guys know what those are. Say my name. Eigenspaces, very good. Now, so he's calling them eigenspaces, W's. Then, I mean, listen, forget his W's, I'm using the E's. Part A, we have V is the direct sum of the eigenspaces. Part B, if you have the sum, let's say j not equal to I of E sub j is equal to E sub I prime, then E sub I prime is perpendicular to E sub I. What I'm saying is the sum of every eigenspace except for the ith one is perpendicular to the ith one. Let me demystify this. In the case of 3, I'm saying E1 plus E2 perp is E3. And I'm saying E1 plus E3 perp is E2. And I'm saying that E2 plus E3 perp is E1. And of course, I probably, to be clear, I want some parentheses in there. Yeah, okay. I'm talking about the perp of the sum. So not only like the complement of the direct sum is also the orthogonal complement, in other words. That doesn't have to happen in general, but it does happen for eigenspaces in the context of normal or self-adjoint operators. That's awesome, because that means that if you look at the projections that correspond to these spaces, right? C Ti is the mapping from V to EI. Is orthogonal projection, and that means that the kernel of Ti, direct sum, the range of Ti is what? The whole vector space, right? But this also has to be, I think in our current context, oh goodness gracious. Well, let me go on. Sorry. I'm getting off track here. C, Ti, this isn't really part of C, this is part of the preamble, my bad. C really starts here. Ti composed with Tj is just Kronecker delta Ij Ti. And D, the identity is decomposed as T1 plus T2 plus plus Tk. And finally, here's the actual spectral decomposition. T is decomposed into lambda 1 times T1, lambda 2 times T2, plus plus lambda k times Tk. That is the spectral theorem. The reason it's called the spectral theorem, as I was starting to say, goes back to the study of spectral analysis, right? Quantum mechanics, discovered around the turn of the 20th century, came with all kinds of questions of like chemistry and understanding the different bands of light that was seen in the spectroscopy. And so one of the initial applications of this math was the eigenvalues being energy levels. And so like the spectrum and spectral theory are it's part of the same story. So one of your homework problems, if you guys want to ask me about it, is about this actually. I'm actually letting you discover or analyze the spectral decomposition for a particular matrix. Like here, let's make up one. Like how do you build these? How do you explicitly build these things in the context of let's do 3 dimensions. It's not too bad. You guys give me an interesting orthonormal basis in 3 dimensions. Can you do that? Well, yeah, not entirely. Not like that. So if I don't add the word interesting, you're just going to tell me the standard basis, and I'd be like, well, that's thanks for nothing. So we don't want that. We don't want that. How about this? V1 is, let's start with 1, 1, 1. That's not going to quite work because we have to do what? Normalize it, right? So 1 over root 3. And then how about V2 is 1 over the square root of 2, 1 minus 1, 0, right? Now I want a third vector, which is perpendicular to both of those. How would you find it? You could guess, right? If I do 1 and 1, I've killed this bird, right? Dot product with that and that gives me a 2. To undo that, I must put a minus 2. And that gives you a square root of 6 for your normalization. There's also this thing called the cross product. You know it. You could do that. But this is faster, right? Yeah. All right. Check this out, yo. V1 transpose. What is this? This is nothing more than 1 over 3. 1, 1, 1, 1, 1, 1, 1, 1, 1. Yay. And if I take V2 transpose, this is 1 over 2, 1 minus a 1, 0. I got to think about this one actually. Oh man. So it's that times this. What is that? 1 minus 1, 0. And then minus 1, 1, 0. And then zeros. This matrix multiplication doesn't get enough airtime, does it? Because this always like weirds you guys out when I do it. Right back at you. Let's see here, V3, at least there's no tortillas involved. Or 3, I need to get some. This is 1 over 6. And it's going to give us 1, 1, minus 2, 1, 1, minus 2, minus a 2, a minus a 2, 4, if I can do my math right. These are the matrices which correspond to projections into the spaces which are, like this gives us, let me call this matrix M1. I'm going to call this matrix M2. I'm going to call this matrix M3, all right? I'm arguing, guys, that, in fact, left multiplication by M1 is a mapping from R3 onto the span of V1. In fact, let's put a J on this, so we're done. These define projection matrices onto those subspaces. They're also commuting. These matrices commute. These matrices are also such that the square of any of them is just them again. Try it out. I'm going to try it out a different way. Vj transpose, Vj transpose is equal to Vj transpose is equal to M sub j. There's my proof. You use your numbers if you want to. I'll keep my letters. Look, the definition of M sub j was Vj transpose. So look at this. They're orthonormal by construction, right? So this is the dot product of a vector with itself, which is the length of Vj squared, but by construction this is 1. So that, which is that. So what I'm telling you is these matrices and the left multiplication operators that they define are basically, these are like the T sub j in the theorem. All right. So look, now you can build a matrix. You want to build a matrix? You guys, you ever build a bear? It's overpriced nonsense, right? But at some point you have children, they'll sucker you into these things. So, let's try it out. Let's make a matrix, right? With eigenvalues. I want to have a matrix A with lambda 1 equal to, let us say, 3, lambda 2 equal to, I kind of like 2 for 2, and lambda 3 equal to, oh, how about 6? That would make it easy, wouldn't it? So if I have A is equal to 3m1 plus 2m2 plus 6m3, what I'm doing, guys, is I'm reverse engineering a matrix with the spectral theorem. I'm building the spectral operators from a given basis. I'm reverse engineering the thing. And the reason I picked 3, 2, and 6 is so that these are gone. And we can just add these 3 matrices. What do we get? One plus 1 plus 1, 3. 1 minus 1 plus 1, 1. I'm doing the top row. 1 plus 0 minus 2 minus 1. Let's see here. 1 minus 1 is 0, plus 1, 1. I'm doing the first column. 1 plus 0 minus 2 minus 1. Well, that's interesting. Look at that. Huh. What's happening? What do you think we're going to see here? Let's see here, middle component. I got a 1, 1. I got 3. I've got 1, 0, minus 1, right? Minus 1, and my 3, 3 component, 5. My claim, this matrix has eigenvalues 3, 2, and 6. And the eigenbasis is the one that we just reverse engineered into these projection operators. What do you think? Is it going to work? I guess I could top hat, but did I say I was going to end class early today? That was, when did class end?
4 or 5.
Dang it. In my heart, I was done 5 minutes ago, though. Does that count? Here's my favorite eigenvector spot. What's the matrix behind me?
3, 1, negative 1. 1, 3, negative 1. Negative 1, negative 1, 5.
Man, I hope this works. I don't know if you'll be able to see it on the camera, but did it work? Where eigenvalues are 2, 3, 6. The 2 is minus 1, 1, 0. The 3 is 1, 1, 1. And the 6 is minus 1, minus 1, 2. I mean, yeah, that's exactly what we were wanting. So now you have reached the stage in linear algebra where you can make the examples if you want.